Hi guys, it's Simon C. Welcome to this new AI radar. Today I have for you 3 news about advances in artificial intelligence. Technology Reviews Will Knight reports that researchers at University College London developed a chess algorithm called Sentimate, which evaluates the quality of chess moves by analyzing the reaction of expert commentators by means of natural language processing. Basically, the AI learns playing chess by reading chess articles. This could help AI programs learn to play the game in a new way. The team analyzed the text of 2,700 chess game commentaries available online, pruning out commentary that didn't relate to high-quality moves. They then used a special type of recurrent neural network and natural language model to pass through them. In accordance with their expectations, researchers found that a bidirectional long short-term memory neural network with pre-trained BERT embeddings yields the highest classification results with 94.2% accuracy on classifying quality data and only marginally lower classification accuracy than the highest classifier for the non-quality data, 78.8%, 0.2% less than non-bidirectional LSTM. Though the results was hardly an AI grandmaster, points out Knight, Sentimate was able to work out some of the basic tenets of chess as well as several key strategies. The researchers say the same learning techniques could also be used one day to help machines analyze sports, predict financial activity and make better recommendations. Furthermore, in the hope of further development of work around sentiment-based chess models, the researchers provide a dataset of about 15,000 annotated moves and their respective sentiment, which they claim is sufficient for the model to outperform a random player and a restrained depth 1 deep chess engine. IBM's Patrick Rock reported that IBM researchers is currently developing HyperTaste, an electronic artificial intelligence assisted tongue that draws inspiration from the way humans taste things, to address the need for the rapid and mobile fingerprinting of beverages and other liquids unfit for ingestion. IBM researchers claim that HyperTaste solves in a portable and rapid way the issue of handling complex liquids comprising a rather large number of chemical compounds and spare users the expensive, time-consuming hassle of routinely sending such liquids to a lab for analysis. To analyze all these chemical compounds, HyperTaste uses combinatorial sensing instead, which relies on the ability of individual electrochemical sensors to respond simultaneously to different chemicals. In that respect, explains Rock, it resembles our natural senses of taste and smell, where we don't have a receptor for each molecule occurring in every kind of food or drink. By building an array of such cross-sensitive sensors, one can obtain a holistic signal or fingerprint of the liquid in question, points out Rock. A mobile app transfers the data to a cloud server, where a trained machine learning algorithm compares the digital fingerprint of the liquid under investigation to a database of known liquids and figures out which liquids in the database are the closest chemical matches, then reports the result back to the mobile app, which displays the result on screen. All in less than a minute from the moment the sensor is dipped into the liquid. One big advantage of having the machine learning models running on the cloud is that the sensors can be rapidly reconfigured from anywhere without alterations to the hardware, explains Rock. To rewire their sensors, user would have to change the parameters of the machine learning models to make them adjust to a new task. Industries and services that would benefit from such a portable cloud-based chemical analysis technology range from industrial supply chains, food and beverages, counterfeit wines or whiskies identification, for example, and environmental monitoring, water quality checks, to the pharmaceutical and healthcare sectors, to name just a few. Recently, Rachel Gordon of MIT Computer Science and Artificial Intelligence Lab reported that researchers at MIT Computer Science and AI Lab indeed have developed an AI system that can learn to see by touching and learn to feel by seeing. So far, robots that have been programmed to see or feel can't use these signals quite as interchangeably. This is the so-called sensory gap. The team used a KUKA robot arm with a spatial tactile sensor called GelSight, a slab of transparent synthetic rubber that works as an imaging system designed by another group at MIT. Using a simple web camera, the team recorded nearly 200 objects such as tools, household products, fabrics and more being touched more than 12,000 times, breaking those video clips down into static frames. The team compiled VisGel, a dataset of more than 3 million visual tactile paired images specifically to overcome the absence of large datasets for understanding interactions between vision and touch, coupled with images generated by generative adversarial networks fed with visual or tactile images. The system achieved vision-to-touch capability by locating the position of touch first, then deducing information about the shape and feel of the region. As for touch to vision, producing a visual image based on tactile data, the model analyzed a tactile image and then figured out the shape and material of the contact position. It then looked back to the reference image to hallucinate the interaction. In the future, argued Gordon, this type of model could help with a more harmonious relationship between vision and robotics. Bringing these two senses together could empower the robot and reduce the data we might need for tasks involving manipulating and grasping objects, said Yunzu Lee, CSAIL PhD student and lead author on a new paper about the system. This method could also prove very useful in robotics, where you need to answer questions like, is this object hard or soft, or if I lift this mug by its handle, how good will my grip be? This is a very challenging problem since the signals are so different, said Andrew Owens, a postdoc at the University of California at Berkeley. Applications may span from object recognition, grasping, better scene understanding, to more generally helping with seamless human-robot integration in an assistive or manufacturing setting, wrote Gordon. Okay guys, it's all for today. See you next time with AI Radar. Bye!